Hi, this video is to show how to run one-factor ANOVA in Minitab. So the data we're going to use is this information about Valencia oranges. Valencia oranges were tested for juiciness at 4 different orchards. 8 oranges were sampled from each orchard, and the total milliliters of juice per 20 grams was calculated. So the higher the number, the juicier the oranges. So we have 4 orchards, and that will be our factor. Orchards, that's the categorical variable. And we see we have 4 levels, call them A, B, C, D. And juiciness is the response variable. And we have 8 replicates in every treatment. This is a balanced design. So N8 and 3 are all equal to 8. So the total sample size N is equal to 32. We add up 8 times 4 is 32. The null hypothesis would be there is no difference in mean juiciness due to orchard. The alternative, there is a difference in mean juiciness due to orchard. In other words, in parameters, that's saying that the 4 means are equal and the alternative, at least one mean, is different. The model is called one-factor ANOVA, and there are these 3 assumptions for one-factor ANOVA: that we have to have approximately normal data, especially with the sample size small, independent sampling, and all 4 standard deviations or all 4 variances need to be equal. Okay, so I'm going to go ahead and bring up the data in Minitab, and here you can see we have all of the response variables, juiciness, in a single column, and we have orchard in a second column, which is the factor. Sometimes you have each population written across, like I might have orchard A, orchard B, orchard C, orchard D, and Minitab will be able to handle data in both those formats. So under stat ANOVA one way, you can see we have 2 options here, and then I've got it set up here where the response and the factor, juiciness and orchard, are in the same in one column, but you do have the second option if you have the data in separate columns. So we're going to run this one right now, and here's what we get. So we get the ANOVA table. Let's start with that. We'll copy and paste that over, paste this picture. And so when you run the ANOVA, you're going to get this. It's an F test, and the F is, again, mean square factor divided by mean squared error. And you can see here that we got 31 total degrees of freedom, which is the sample size is 32 minus 1 is 31. 3 degrees of freedom for the orchard, because we have that's K minus 1, 4 levels minus 1 is 3, and then the difference to get the degrees of freedom for the air. And then the sum of squares divided by the degrees of freedom is the mean square, and mean square orchard divided by mean squared error is 7.31, which has a p-value of 0.001. So that's an F distribution with 3 and 28 degrees of freedom. Okay, so my decision here would be that the p-value, right, is equal to 0.001 less than alpha 0.05. So that means we're going to reject the null hypothesis. Right. So the conclusion would be there is a difference in mean juiciness due to orchard, right? So there's my conclusion. Right, there is a difference in mean juiciness due to orchard. Now, if we actually go back to Minitab and look at those means, let's go back to the Minitab file. We get a couple things here. First of all, here's the actual data. Let me copy that. Let's actually just look at that here. So you can see the means, the sample means are different. It looks like orchard C has the highest sample mean, orchard D has the lowest. And if you look at this plot, you can see, okay, it looks like orchard C has got the juiciest oranges, maybe these 2 down here. But now we want to look at this a little further. So we want to say, okay, there is a difference, but which orchards are different? Which orchards are different? So we want to compare all the possible pairs. So I want to compare orchard A to orchard C, A to B, A to D, and so on. There's actually 6 pairwise comparisons that you can make from looking at these 4 groups. And in order to do this in an honest way, we run the Tukey test. And Tukey test tests it does all multiple comparisons at an overall significance level of 5%. So how you do that in Minitab, if we want to run the Tukey test, we go stat ANOVA one way again, and then we go to comparisons. And under comparisons, you click that you want the Tukey test right there. Alpha goes right here, so alpha is 5%. If you were doing the test at 1%, you would change that to a 1. But we're doing alpha 5%, so I'll just leave it like that. And when you run it, you get this grouping, and we're going to use the grouping. I think the grouping method is I'm just going to bring this over. And we'll bring that to the other page. Okay, so these are called pairwise comparisons, running at an overall risk of 5%. And so it says that means that do not share a letter are significantly different. So if we want to think of this, we can say, okay, orchard C and orchard A are both in group A. So let's just say that we'll call that the red group. Orchard A is in the C and A are in the red group. And then let's call grouping B the blue group. And so there are 3 orchards, A, B, and D, that are in that group. And the rule is that means that do not share a letter are significantly different. So here we can see that C is different than B and D. But really, there are no other significant differences, right? B is different from C and D, and there's no other significant differences. So that's how we would write our conclusion, right? We would say that, let's write it down here, right? Based on this output, I'll just say, okay, orchard. So my overall conclusion would be oranges from orchard C have more juiciness, more mean juiciness than oranges from orchards B and D, right? Because they don't share a common letter. But A isn't different from anybody because A is in everybody's group. So then we would also say there are no other significant differences. So all the other pairs we can't say are significantly different from each other. And that is how you run ANOVA in Minitab.